But there's several other things that very fast.
Looking forward to your talk.
Thanks.
We're just giving talks before that.
Yeah, so it's
Thanks. Please do.
How are you doing? Well,
I'm pretty good. How are you? What is your name? I'm Christine Jones.
I work in high energy.
Okay.
I also do a lot of stuff for AAS right now. I heard you give a talk last summer?
Oh yeah, last summer during the undergrad program. Yeah.
Yeah, I take care of the RU undergrad one too.
Okay.
Yeah, along with John Greene and Marie Malkachek, who is now finally officially sort of retired. So Matt Ashby's helping in that one instead. You'll wait till after your talk to eat?
Yeah.
Good idea. They moved back. I moved up. So whatever. You can still have your seat, yeah. What year are you in as far as being
I'll be in my second, about a year and a half.
Okay, so
It's coming June, yeah.
So when I heard you last summer, you had just arrived.
It was about a year. Yeah.
And is this a 3-year or a 4-year?
3 years. It's going by fast.
Yeah.
I'm working with a number of people in the star formation community. I'm working with Charlie Latta, and I'm doing cosmology work with Avi, and I'm been collaborating with other postdocs in the ITC.
I plan to look seriously because for other reasons I've noticed that, and I've known it kind of for a long time, that sometimes when postdocs come, if the amount of postdoc is being hired by a particular grant that a person has, that sometimes they don't get very well integrated and don't end up working closely and don't really build collaboration skills. And it's really bad. And
I've had a great time so far. And
Good,
I've
good.
been lucky to
I'm
be
glad.
surrounded by lots of good people.
it's great, yeah.
Yeah.
But, so I'm sort of poking around and like looking up people and looking up their papers.
Okay.
And getting worried when they don't have co-authors.
I see.
And they've been here for a few years.
Yeah.
It's not a good sign, right?
Yeah.
So I'm actually thinking that in some cases we need to have more mentoring. Maybe not even somebody to work with, just somebody to watch out. Anyway, you're on.
I don't think the food here is good. It's just that people are more interested in the ITC Luncheon. Using this very easy. We just had an excellent ITC colloquium by Greene, who is sitting over there. She's currently a professor at Princeton. Used to be a graduate student here. So she went all the way, not so far away actually, but she's coming back to tell us what we should know. We learned about black holes, and she will talk in a few minutes on elliptical galaxies in different contexts. The first speaker today is Imara, who is a postdoc here at Harvard, more generally, but also at the Center for Astrophysics. And she will talk about a personal subject between me and reionization. Intergalactic dust. Then we'll hear from Jenny about gas and massive elliptical galaxies. And after that, we'll hear from a visiting graduate student, Margalit, who's visiting us from India. And he will talk about accretion flows following white dwarf neutron star mergers. And finally, we'll hear from Zolotukhin, who is visiting us from IRAP over there. And he will tell us about the slowest spinning X-ray pulsar in extragalactic globular clusters. Mia.
Thank you, Avi. All right, well, between you and galaxies, from the very near all the way up to the epoch of reionization, there is dust. It's some of the rarest material that exists in the universe, and yet we have to think about it because it can interfere with our measurements, such as the distances to standard candles, the consequent measurements of the cosmological parameters, and the galaxy luminosity function. So I'm very pleased to tell you about a paper that I wrote with Avi in which we place new limits on intergalactic dust, from the local universe all the way up to the time when the first stars and galaxies began reionizing the intergalactic medium. In the interstellar medium of our own galaxy, we know that light is attenuated and reddened by dust, and that longer wavelengths undergo less extinction. And by modeling extinction curves along different lines of sight, we also know that the amount of extinction is sensitive to dust grain properties, such as the size and the composition of particles. And this phenomenon of extinction occurs in the space between galaxies as well. So to begin with, we believe that dust gets into the intergalactic medium, the IGM, via galactic winds, such as those by population 3 stars, supernova winds, and other galactic winds. A number of studies have modeled the enrichment of the IGM with metals, and most likely the same winds that carry metals into the IGM also entrain dust. In our paper, we begin by showing how the evolution of the optical depth due to dust depends on the metallicity of the IGM. So the standard expression for the optical depth is pretty straightforward. It depends on the volume density and the opacity of the particles and the distance to the source. Now, obviously, we don't know what the volume density of intergalactic dust is, but the proton volume density is very well constrained. And the two are related via the dust-to-gas ratio of the IGM, which is in turn linked to the metallicity. Now, the wavelength-dependent opacity is, of course, the other big unknown. In this case, we can test different distributions of the opacity based on different galactic models of the extinction curve, shown here. The extinction curve, or the reddening law, shows how the wavelength dependence of extinction is sensitive to the properties of dust grains, as I mentioned before. So for instance, if a dust cloud is dominated by small dust grains, the extinction curve will have a steeper slope and a smaller value of the selective extinction, which corresponds to an overall higher value of the opacity. Now, we were also interested in exploring the evolution of IgM metallicity, which correlates with the dust-to-gas ratio, since most heavy elements are expected to be locked up in dust. But instead of adopting a strictly linear relationship, we adopted a functional form that was derived for nearby galaxies having a wide range of metallicities. Now, we were especially interested in the dust-to-gas ratio at very low metallicities, since the IgM is expected to have a low metal abundance. So with these ingredients, the optical depth versus redshift, as expected, increases as you look at sources further back in time and as you get more intervening material between you and the source. The black, red, and blue curves are for 3 different observed wavelengths, and the vertical lines mark the redshifts beyond which Lyman alpha absorption obscures our view. So photons that started out in the UV at high redshifts and can make it all the way through the IgM to us are redshifted to micron wavelengths by the time that they reach us. Now, we also show curves for different values of the selective extinction, for different values of RV, and you can see that the differences in the calculated optical depth really only start to matter once you get to very high redshifts. Overplotted as well, we have data from the literature. These are extinction measurements from galaxies and quasars. And you can see that since these curves are for solar metallicity, the optical depths derived here are too high and they rise above the observed data. But if we lower the dust-to-gas ratio until this blue curve passes through the last data point, we can put an upper limit on the metallicity at z equals 10 around the time of the start of reionization. And in this way, we found that the metallicity of the IgM at z equals 10 should be no more than about 10% solar. And with our assumptions, this is equivalent to a dust-to-gas ratio of about 3% of the value in the local interstellar medium. Now, we did this for all of the redshifts where we have extinction measurements and put a limit to the intergalactic dust-to-gas ratio at different periods in the universe's history. But we can do better than this and fill in some of the gaps in this plot. So for a given source, the optical depth at lower redshifts has to be less than the optical depth at the source. Therefore, we can derive the DGR for redshifts less than z source, assuming that optical depths at all these lower redshifts are less than tau at z source. So the curves shown here provide further constraints for redshifts where observations don't exist. So to conclude, it isn't trivial to disentangle reddening due to dust within the ISM of galaxies to reddening due to IgM dust, and we know very little about the composition of dust at high redshifts. But our results show that it is possible to constrain how dust impacts our measurements. And with ALMA, as we're starting to find out more and more high redshift galaxies with larger dust-to-gas ratios than we might have expected, we're learning more and more about the nature of early star formation. And finally, another application of our work is that we can calculate the degree to which infrared emission from dust expelled into the IgM by galaxies, such as this one, how the dust emission conceals distortions in the spectrum of the cosmic microwave background. And we did just that in a paper that went up on AstroPH this week. Thank you.
Question is how much it contaminates in addition to galactic dust, CMD
core collapse supernovae. When you're looking back, not to the very beginning, but after 10 to the 8, 10 to the 9 years, can you tell something about when type 1a supernovae kick in?
That's a very interesting question. I've thought about it, but I think for me at least it seems more conducive to simulation. So I'm very interested in looking at Illustrious, for instance, and looking at the details of when we get the bulk of dust being emitted from these galaxies.
I have a question regarding low redshifts. I haven't seen a number what the reddening should be, what the expected reddening should be at redshift, let's say 0.2, 0.3. But we know that at those redshifts, the colors of elliptical galaxies are very well calibrated. So do you think we can use it in order to leverage the value of the optical depth?
I hope so. I think that's a good idea. And I agree with you, to better constrain these lower redshifts. The most recent detection that we found was at Z equals 0.5. And so this point here is actually the only actual detection, whereas the others here are upper limits on the optical depth. But yeah, I agree that would be a good thing to do. Right.
Any other questions? If not, let's continue again. Aside from being a brilliant astrophysicist, she's also an artist. Invite everyone to check out her art online.
Hello again. It's always a pleasure to be here at the CFA. I think the last time I spoke here, Chungpei and I were just starting our survey of massive elliptical galaxies, so it's a pleasure to have the opportunity to update you with a brief advertisement of some of the exciting things we're doing, and today I'm just going to focus actually on the gas content of these galaxies. So massive, massive, it doesn't stand for anything. This is an IFU survey of the 100 most massive galaxies within 100 megaparsecs. Lots of goals. We basically want to study all the dark components of these galaxies using the kinematics on large scales to probe the dark matter halo masses, and then zooming in on the very centers to get the supermassive black hole masses using the optical spectra to constrain the stellar population histories of these galaxies. What I want to emphasize here is just that we are extremely complementary to existing IFU surveys, in particular Atlas 3D, which was volume limited to 40 megaparsecs. Because we go out to 100 megaparsecs, we're really filling in the most massive galaxies in the universe today. So that's our main goal. I'll just briefly say that we apparently showed up on NPR last night. This is our first supermassive black hole mass, 17 billion suns, and it lives not in the center of a massive cluster like Coma, but rather a moderate group. So we're very excited about the prospects of using massive to probe the full distribution of black hole mass at the high stellar mass end. But what I want to focus on today instead is the gas content of these elliptical galaxies. And we're quite interested in understanding, first of all, where does the gas come from? To what extent is it accreted from, intergalactic space? And to what extent are we really probing internal mass loss processes? The next question to understand as we look at the gas content of these ellipticals is how well do they retain their gas? What is the role of both stellar and black hole feedback in regulating how much gas these galaxies contain? And what's the importance of the angular momentum content of the stars when it comes to how much gas we see? And then, of course, in order to understand our observations, we really have to understand what's exciting the gas. Now, of course, in massive ellipticals, they're famously red and dead, so they don't contain very much cold gas. Most of the action in terms of the mass is in the X-rays. And lots of people in this room are far more expert than I on the X-ray properties of local ellipticals, but I want to start by advertising a paper that Andy Goulding led. He was a postdoc here before he came to Princeton to work with me, and we've really been filling in the high mass and looking at the X-ray halos of individual galaxies. So I want to start there, but we've been looking at all the gas phases in these massive galaxies, from the warm ionized gas, which we can probe with our IFU data, all the way to the cold molecular gas, working with Tim Davis to look for CO in some of these galaxies. And of course, this is interesting both from the perspective of the star formation histories of the galaxies and also their merger histories, but also we're real interested in using this CO ultimately to get an alternate measurement of the black hole masses in these galaxies. So just, again, this is going to be at the level of an advertisement, but almost all the important work that's been done looking at hot X-ray halos in individual galaxies has been done here. And in the sort of schematic, you see the Kim and Fabiano work, which basically used Atlas 3D to look at the X-ray halos of local ellipticals. And they sort of divided things into this low mass rotating elliptical family and then a higher mass non-rotating elliptical family, because they had very few of these high mass non-rotating galaxies. And so our big contribution was really to fill in the very high mass ellipticals and to be very systematic about looking at the X-rays only within the effective radius of the galaxy. So as you go to more massive galaxies, of course, you probe a wide range of environments. Big clusters have extremely large X-ray halos. We're not looking at that gas. We're really looking, particularly in the left, at the gas that falls within the effective radius in this white circle. Okay, and when you do that, you actually see that in this pure X-ray luminosity to X-ray temperature plane, the galaxies, the individual halos follow one track. Okay, they're considerably steeper than what's seen for clusters. That's the relationship you expect just from virial arguments. So something is depleting the gas, we think, systematically as you get down to these lower mass halos. And I believe Frika van de Voort had a paper on the theory of this just come out today. To understand the origin of the gas, you want to try to link the stellar properties with the X-ray properties. And these are just two well-known ways to do that. So the stellar mass and the stellar velocity dispersion of the galaxies against the X-ray luminosity. And what you see is that there's a tremendous amount of scatter. So neither the halo mass nor directly the stellar mass uniquely tells you what the X-ray halo will look like. And you can see a pretty strong dependence on temperature. So at a fixed stellar mass, the coldest galaxies have the lowest Lx and the hottest ones have the highest Lx. So then we just went from there to look at the relationship between the velocity dispersion and the temperature of these X-ray halos. And we find actually that it behaves as you would expect for virialized gas. So temperature is going as sigma squared, but parameterizing these with this beta parameter, we find that all the halos are a little bit hotter than you would expect. So this bottom dashed line is virial. Everything is just a little bit hotter. This has already been seen in more detailed observations of individual systems by Buett and Humphrey and others, but we're now seeing it in a large sample. Furthermore, we see no correlation between the radio power and the temperature in this plane, or the amount of rotation, or the halo mass. So it's not completely obvious to us what is driving the scatter in temperature at a given fixed galaxy potential. Final result I'll flash. This is asking again this question of where does the gas come from? And if you just take a naive model for stellar mass loss that assumes that all the galaxies have the same age, this dashed line is what you would expect to see, a relationship between velocity dispersion, stellar mass, and X-ray luminosity. And you can see that it doesn't do a terribly good job. And from the Atlas sample alone, Mark Sarzi posited that the rotating galaxies, those with high angular momentum, were least able to retain their gas. That by itself, when we add the massive galaxies, does not completely explain this discrepancy. Instead, we see that you have to sort of postulate a wide range of stellar mass losses to explain what we're seeing at the high mass end. So that's all I'll say about the hot gas halos. Just briefly to flash what we're looking at with ionized gas. This is work that Viraj Pandya has been doing with me. He's my student at Princeton. He's on his way, I think, to Santa Cruz for graduate school, so we're pretty pleased. So this is one of our most spectacular systems. What you can see is that there's a really nicely defined sort of kiloparsec scale ionized gas disk. This is the big red and blue circles. It's nicely rotating, but it's 90 degrees offset from the rotation of the stars, which you see in the underlying color scale. So this is one of these examples of probably a recent merger that brought in some cold gas that is counter-rotating. And just asking what fraction of the galaxies in the massive sample have these well-organized ionized gas disks will give us some handle on the merger histories of these galaxies. Turns out to be a very strong function of velocity dispersion. So at the very highest masses, we rarely are detecting even this ionized gas, and then the detection fraction goes up dramatically as we go to lower stellar velocity dispersions. Just very briefly to end, we've also been surveying the CO content of these galaxies. We started out looking for things with an excess in 22 microns versus K-band, suggesting extra gas and dust. We've already heard about dust today. So we went and looked, and 6 of our 11 first targets had beautiful rotating CO gas disks. Now Tim Davis is looking quite systematically at the gas properties of all of these galaxies. The sort of tantalizing first result is that the Tully-Fisher relation for ellipticals is offset by a considerable amount relative to what you see in spirals. So this is the Atlas 3D points in black, and then our addition in red, and the dashed is what you get for spirals. So I'll leave you with that tantalizing result, and that's my sort of advertisement for the gas content of massive elliptical galaxies. That's right. So you're talking about the X-rays, right? So I think, and people in this audience know better than I do, but I think that the cooling time for things that are considerable outliers in their X-ray temperature is short. But then to get from this a little bit of extra heating down to virial, those cooling times become long. So I think they can stay in this state for quite some time. I went too fast, but I'll be here all day, and please come talk to me if you're interested in hearing more. Everything is completely clear. That's all right.
All right. Hi, thanks for having me here. So I'd like to talk about recent work that I just finished with Brian Metzger at Columbia, in which we studied the accretion flows following white dwarf neutron star mergers. So just a basic background, the scenario that we're dealing with is the following. You have a compact binary system, in this case a white dwarf and a neutron star, that slowly inspirals due to gravitational wave emission. And at some point, the white dwarf, which is relatively extended, overflows its Roche lobe, And if it's sufficiently massive, then it will proceed in an unstable mass transfer, in which case it will essentially be disrupted and sheared into an accretion disk. This is kind of the formation scenario of the accretion disks that we're interested in. And it turns out that the rates of these mergers are actually quite high. So they're of order 10 to the minus 4 to 10 to the minus 5 per Milky Way-like galaxy per year. These are observationally inferred. And so this is comparable to the neutron star merger rate, for instance. And yet these systems have received very little attention in the literature, definitely compared to the extensive study of neutron star mergers. Okay, so that's just a bit of background. A few characteristic numbers to keep in mind about these accretion flows. So the characteristic radii of these accretion disks is of order 10 to the 9 centimeter. You can read this off this black curve. This shows these characteristic values as a function of the disrupted white dwarf mass. It's not surprising, that's basically of order the white dwarf radius itself. But more importantly, the characteristic densities are quite high, 10 to the 5 gram per cubic centimeter, which means that photons are essentially trapped. So this is a radiatively inefficient accretion flow. So as many of you know, there are a myriad of models for these types of accretion flows, some of the most important of which have been developed right here by people like Ramesh and collaborators. So we model our accretion disk as sort of an adios type disk, in which basically posits that in the absence of radiation, the disk cools itself by emitting outflows that carry away mass and energy. Another important number to keep in mind is the temperatures in these disks, which are very large. So you reach temperatures above 10 to the 9 Kelvin, which basically tells you that nuclear burning is inevitable. So you get nuclear fusion inside these accretion disks, and that's an important ingredient to take into consideration when modeling these. All right, so this is kind of a laundry list of all the ingredients that we take in our model. I won't go through all of these, but it's basically a 1D vertically averaged Shakura-Senev alpha viscosity disk that incorporates nuclear reaction network and some prescription for the wind cooling, the outflows. So this is admittedly a very simplified approach, but since this is of order, first order approach to this problem, it's kind of justifiable. Furthermore, this allows us to very extensively explore the parameter space, sort of as a prelude to more detailed numerical simulations, hopefully. All right, let's go over a few key results. I won't have time to go over all of them, but let's look at a few. So let's look at carbon-oxygen white dwarfs to begin with. The first thing that you notice is that you get a very rich composition inside these accretion flows. So this figure illustrates the mass fraction of different isotopes inside the accretion disk as a function of radius. And you see that you get sort of an onion skin profile, kind of resembling evolved stars, where at sequentially smaller radii you burn heavier elements. So you start with your initial carbon-oxygen material, and around here you start burning into neon, magnesium, successively higher elements until you reach iron, nickel-56. And at even smaller radii, you photodisintegrate. The temperatures are so high that you photodisintegrate these ferrum group materials into alpha particles and free nucleons. This is a very rich composition that you get. Furthermore, nuclear burning is not just important on the nucleosynthesis inside the disk, it's actually dynamically important on the disk. So nuclear heating from the reactions themselves are as important or comparable to the viscous heating of the disk. So you can see that as the red curve here, where around the carbon burning front, for instance, you get of order unity contribution to the heating rate from the nuclear burning itself. Actually interesting, if you note this small dip to negative values, that actually tells you that nuclear reactions are cooling the disk. That just has to do with the photodisintegrations. So those are actually endothermic. They cool the disk at small radii. But in any case, the nuclear reactions are important on the dynamics, not just the nucleosynthesis. So this is all kind of consistent with the picture that we already knew from steady-state model of these disks from Metzger 2012. But what happens when you include the temporal evolution? So it turns out that you get sort of a self-similar evolution of the composition profiles. And as you'll see sort of a movie here, or a sequence of snapshots, you'll see that the composition profiles basically shift, kind of retain their morphology and normalization. They just kind of shift to larger and smaller radii as the accretion disk evolves. What happens is that at early times, the accretion rate increases in the disk, and hence the temperature increases, so you can start burning the same matter at larger radii. But at late times, after the peak accretion rate, the temperature decreases, and therefore you need to move into smaller radii to get to the same temperatures and burn the same matter. So you can see this in the following sort of snippet. So this is of order the peak accretion time. And this whole pattern just kind of shifts in and out. sort of self-similarly. And this is very robust to all of our model parameters. We changed basically anything we could in our simplified model. This picture, at least qualitatively, stays very much the same. That just has to do with the strong temperature dependence of these nuclear reactions. Okay, what about the outflows from these disks? So over here you can see the cumulative mass distribution of the outflow as a function of the outflow velocity. You can also read this from the top axis as the radius, the disk radius from which the outflow was ejected. And you see that you eject basically of order the initial white dwarf mass in outflows. So we kind of eject most of the disk mass out. That just has to do with the model, the kind of adios type model, which basically requires that you eject a lot of mass to cool the disk. And the characteristic velocities are of order 10,000 kilometers per second. This is kind of average velocity. And most of the composition of this outflow is basically your unburned carbon-oxygen matter. But you can get some very interesting signatures from the nucleosynthesis inside the disk, in particularly of order 10 to the minus 3 solar mass of ejected nickel-56. All right. Let's look a bit at what happens with helium white dwarfs. So you have a very similar picture in terms of the nucleosynthesis inside the disk. Nuclear reactions are also very important on the dynamics, even more so than in the carbon-oxygen white dwarfs. But something is qualitatively very different in the helium white dwarf composition, and that is that you have to go through the triple alpha bottleneck in order to generate this nice nucleosynthesis that you see here. So this is a snapshot of around the peak accretion time, and you see that you start getting triple alpha around here where you form carbon-12, and then you can successively alpha capture onto these carbon seeds and form your higher mass elements such as calcium and nickel-56. But the reason this is fundamentally different than the previous case is that the triple alpha reaction is very density dependent, as opposed to the other reactions which are mostly temperature sensitive. And what happens now is that at early and late times, when the disk density is quite low, the triple alpha becomes very ineffective, and so the nuclear burning inside the disk essentially shuts off completely. So you can see that in this sort of movie over here. This is kind of an initial time, and you see that you have mostly just your helium composition. And as the peak accretion rate increases, the density increases, you get effective triple alpha. But at late times, again, the triple alpha can't do really anything. You kind of lose your carbon seeds on which you can alpha capture, and you revert back to almost a pure helium composition of your disk. This is kind of different in terms of the temporal evolution. All right, I'll skip over hybrid white dwarfs. So what are some implications of these accretion flows? Why are they interesting? So probably the most important point is what kind of optical or electromagnetic transients you can expect to get out of these. So from the outflows that you get out of these disks, you can expect some sort of optical transient that will peak on timescales of order a week. Now, if these transients are powered solely by the nickel-56 radioactive decay, then you get quite dim events of order 10 to the 30 erg per second. That just has to do with the quite modest nickel-56 yields in our outflows. But here we actually propose that these events could be powered by winds launched off the accretion flow at late times. So these are shock-powered or interaction-powered, in which case you get much larger luminosities of order 10 to the 33 erg per second. So these could maybe be progenitors of systems such as supernova 2002 BG or the Pan-STARRS rapid supernova-like events. So these are all events that have very short timescales and kind of peak luminosities of this order of magnitude. So this is kind of just an estimate right now, but we're working on getting more detailed light curves and simulated spectra, so this is something that you can look forward to in the future. In terms of the nucleosynthesis inside the disk, so this summarizes the yields in different isotopes that have been ejected from the accretion disk. So each curve here, each colored curve is for a different model. And you can see that these are relatively robust, except for, unfortunately, the nickel-56, which has quite a large spread here as well. But again, you emit of order 10 to the minus 3 solar mass of nickel-56. Possibly more importantly, you emit only of order 10 to the minus 2 solar mass of calcium. The reason this is important is because these systems have previously been proposed as progenitors of the calcium-rich gap transients. But we find that this possibly cannot explain most of these transients just due to the large inferred calcium masses. But again, you may get explosive burning in some of these models, in which case you can produce much larger calcium abundances. Just the last note, you can ask what is the impact of these accretion flows on the central accreting neutron star. So it turns out that since most of the matter is ejected in outflows and winds, only a very small amount, of order 10% of the disk mass, is accreted onto the neutron star surface. So first of all, it's quite unlikely to expect these neutron stars to collapse. This is of order 1% increase in their mass. But importantly, you can spin up the neutron star to spins of order 10 milliseconds. So this might be a new channel to form isolated recycled pulsars. That had already been proposed in the early 80s by some authors, but has kind of been forgotten since, at least from as far as I know. All right, so this is a very brief recap, but if you have any more questions or like to know more about this, you can come to me later. Thanks. Sorry, is it different then? Oh, no. Yeah, so I forgot to comment about that. It's exactly the same if you put a black hole instead of a neutron star. The only thing you need to consider is that the black hole needs to be a stellar mass black hole. If it's more massive, then the white dwarf will probably not disrupt. So, yeah.
So, thank you. I thought this was very interesting. Could you expand on the origin of the very high temperatures in these disks? Because the material inside the white dwarf is actually relatively low entropy material.
Mm-hmm. Right. So this is just basically, it's viscously heated. So it reaches temperatures of order the Weyl radius. These are kind of thick disks, so their scale height is of order the radius. H over r of order, a half or so. Sorry? No, the cooling, the densities are not large enough to be cooled by neutrinos, so that's why these are also radiatively inefficient both in photons and both in neutrinos. And that's why we assume that they cool through outflows. Yeah.
So when the white dwarf is disrupted, it might actually give you a disk with some ellipticity, which in principle could lead to additional mixing in the disk. Do you have any sense, like if you introduce some additional mixing, how that would affect things?
So we changed the chemical mixing, sort of the mixing of the different isotopes in the disks. That's kind of a free parameter in our model. And we changed that, and the picture stays very much qualitatively the same. You do change the yield somewhat, so part of basically the profiles kind of diffuse upstream. They can't diffuse downstream because of nuclear burning, but they can diffuse upstream. But the basic results are pretty much the same, yeah.
So what's the accretion luminosity on the neutron star?
The accretion rates, so the outer accretion rates, or the mass loss rates from the disks, reach peak accretion rates of order 10 to the minus 2 or 10 to the minus 3 solar mass per second. But only a small fraction reaches the neutron star surface, so of order maybe 10% or less than that. But it's, yeah, very large accretion rate.
Very super.
Yes, definitely. Yes.
In terms of the rates of these fascinating events, when you gave the number at the beginning, was that based on the numbers of neutron star white dwarf systems that are observed in the milky way?
Yes, exactly. So there are, I think, about 20 white dwarf neutron star binaries known in our system. These are all observed as pulsars. So actually the rates could be higher if you have systems like these in which the neutron star is not a pulsar. But yeah, I think of those, if I remember correctly, 4 will merge within a Hubble time of those 20. Yeah.
No more questions? Let's stand then.
Thanks.
Hello, everyone. Thanks for giving this opportunity to talk today. I'm going to cover the recent work of our team, a particularly interesting object, which happened to be discovered very far away from our galaxy, at least by the X-ray astronomy standards for these sort of objects for X-ray pulsars. Let me, oops, it stopped working, okay. Let me briefly introduce you to the pulsar recycling concept, or remind you if you're aware of it. So neutron stars are thought to be born quickly rotating, and then they slow down in rotation-powered phase, being observed as a radio pulsar. So basically, from normal pulsars, lost my track. So they slow down till 1 to 10 second periods, and at the same time we know that in global clusters X-ray sources are observed very often in millisecond pulsars. So they dominate X-ray content of global clusters, and these are millisecond pulsars rotating at hundreds of hertz. We now think that they used to be in accreting binaries, and this leads us to the thought that the accretion first it buries magnetic field, and then it spins up the neutron star from 1 second to hundreds of hertz, basically from 1 hertz to hundreds of hertz. And after a well-known discovery of highly super Eddington source in M82 Galaxy, I found myself working on something I call Pulsar Factory, on software that would help me to check other luminous X-ray sources and find pulsations which would support the idea that they are neutron stars, and there are a lot more super Eddington neutron stars out there. And what we did, we built a very large database of 50 billion photons, basically all photons registered by the X-Newton Newton satellite since 15 years of its operation. And we wrote a pipeline that searched for coherent pulsations, essentially by right ascension declination. And the software does timing analysis, so it constructs power density spectra of small data chunks, and it does another coherent test for timing. And if frequencies of both independent tests match, it goes further, launches another coherent pulsation test, and essentially in the end sends a text message to an operator. And we were unlucky to choose an Andromeda Galaxy as a test sample, because we discovered something which we didn't expect. And well, like this, here is a frequency, here is a power spectra for 2 independent observations. Here's another test, and that's basically output of Pulsar Factory that we saw once after checking all photons from Andromeda Galaxy. And when we looked at the position of this object, of this X-ray source with pulsation around 1.2 seconds, we found that it projects on a very large and dense global cluster at the outskirts of Andromeda Galaxy. We were lucky to have it at the edge of view of the HST exposure. And here's the basic data. So it's a quite bright pulsar, accreting at up to 30% of the Eddington luminosity with spin period around 1 second, and it seems to be associated with this global cluster, because the chance superposition probability is around 10 to minus 3. It is 10 times slower than the formerly known slowest accreting pulsar in global cluster, which is a pulsar in 2005 source. So here's a brief comparison. So it spins, the luminosities are equivalent, but our pulsar spins at 10 times slower than the previous one, and hence, because this one is called mildly recycled, not yet millisecond, but on the way to millisecond pulsar, so this beast which we discovered is hence non-recycled one. It was very extraordinarily difficult to measure its spin up. Here's the spin period of a neutron star, here's the epoch of observations, because at this photon statistics, when we have like one photon every few seconds, and only each fifth of photon comes from the neutron star pulse, none of the existing algorithms work with this, but by combining data sets in 9 groups, we're able to measure the spin up, except for essentially for this point, for the latest observation, because this one we can discard because of the large error bar. But this poses a question whether, in fact, neutron star is spun up. If it is the case, if we think this is if we forget this point, yeah, then it leads us to a conclusion that the B field is closer to the value for millisecond pulsars. If it rotates in equilibrium, so it will reach some sort of plateau, the B field is much larger, it's 10 to the 12. And both scenarios are very interesting, because if it's spin up, then field decayed too quickly, because we see a typical value for millisecond pulsars, but we have 2 orders of magnitude slower rotation. And neutron star didn't accrete that much matter. If it's in equilibrium, we have an apparently young neutron star in a 12-year-old global cluster. Folks that do studies of sophisticated studies of modeling of binary systems in global clusters, like Ivanova, say that there is a very valid scenario to create young neutron stars in a global cluster of any age, which is called accretion-induced collapse, where when one dwarf accretes matter from a companion and converts without big explosion, without getting a kick, converts into collapses into neutron star, and they say that this process is 3 times more efficient than any other dynamical event in global cluster that creates LMXB. So the rates of accretion-induced collapse formed LMXBs in global clusters are quite high for dense systems. And then we compared the host of mildly recycled pulsar in 2005 with the global cluster which hosts our pulsar. And indeed, these are very old, very huge clusters. Probably both are nucleus of former dwarf galaxy, stripped of nuclei of dwarf galaxies. This one has a very large core. And if we compare encounter rates, the metrics which is known to correlate with number of LMXBs and reflects the number of close encounters in global cluster, 2005 is the #1 global cluster in the Milky Way galaxy by this parameter, and our host global cluster is even more, has more encounters per unit time, and same for this small gamma specific encounter rate, which shows how many binary disruptions or binary exchange events happen in global cluster per unit time. So I'm saying that 2005 is known to be very prolific. It has a huge population of radio pulsars and LMXBs, and M31 BO91D is even more prolific. So I come to my conclusions. XBO91D that we discovered is the second farthest extragalactic pulsar. It is the slowest spinning neutron star in global clusters, and probably first non-recycled accreting binary. And despite that it looks peculiar, I think accretion-induced collapse origin in a prolific global cluster can explain what we observe. The last thing to note is that I'm happy that this research is one of the few that can be reproduced online that I showed at my talk yesterday. In a couple of minutes, everyone can rediscover this pulsar or discover a new one. So I welcome you to try xmm-catalog IRAP.pu, and there are a lot of new science to be done just by mouse clicking. Thanks.
Well, one comment and then mainly a question. You know, if it's not spun up as much as other pulsars, that could also speak to how much material was accreted. And you do have something unusual on the binaries. So this would be worth discussing, I think. But in terms of the question, this is really exciting because one of the early Chandra results that we came up with in M31 and other galaxies is that on average there was a population of brighter globular cluster X-ray sources than in the Milky Way. And the question that we were playing with is, are they black holes or are they neutron stars? Now you've just established that one is definitely a neutron star. So the question is, how much more of this can you do with this method? And also, would you be sensitive to X-ray bursts that would also be able to find, distinguish between neutron stars and black holes?
Well, M31 is a very nice object for this sort of studies. The problem is that it's too far for current generation of X-ray instruments, so the phonostatistics are low. Despite of this, I have on my table I have few more pulsar candidates, but even this one required terrible amount of work. I mean, it's not, you can't use conventional timing analysis software with this. And this one was the easiest to analyze because it popped up in 3 observations immediately. So I have more detections of neutron stars, pulsating neutron stars from M31, but they require a lot of work. As for that X-ray bursts, like type 1 X-ray bursts, there are tens of them in the Pulsar database. So if you come up with a project, I've just seen it. You just need to bin light curves and the infrastructure is there, and I can do it very quickly and easily. So this is a nice thing to do. Yes.
Well, a question about the position. I'm possibly over-interpreting the figure you showed, but is the apparent offset from the center of the globular cluster?
It's not clear because it was always the smaller circle is in fact XMM one, because XMM covered this field much many more times than Chandra, and for Chandra the red one it is at the edge of view. So there's no very significant constraint if it's outside of the core or inside. So both options are possible in fact, but they don't really help interpretation, because half of the neutron stars, even in binaries, sit outside of the core at this age of the global cluster. So it can happen. Yeah.
Did you say the binary period was 30 days?
No, 30 hours. Sorry, I didn't mention yet. So it's So it is again the widest known binary in global cluster.
Thank you.